But the goal will be to just walk through one example and see how can we model it, right? How can we model the number of days of absence? Is it reflective of it? Can we capture anything that underlies in the data set or not? So this data set, as I said, is taken from, sorry, I said UC Berkeley, but it's hosted in UCLA, not Berkeley. This is UCLA data set. What is this data set? So this data set is of 314 high school juniors. This is equivalent to a 10 standard. And what we are looking into are basically just three variables. One is the days of absence. This is urban area. The response variable, which we'll talk about what is the response variable. We talked about it in the last class, but I'm going to talk about it again. We will look into what happens in terms of the absence. The number of days that you're absent, that is what we are going to model. We want to see what factor explains it. Now, in an ideal world, you would want to measure everything about a student. You would want to measure what is going on in their life, how is their health, and so on. And of course, this data set is not complete. The only two variables that you have is what academic program they are enrolled in. They could be in a general program, they could be a vocational program, and there are different connotations of it. We'll study this in just a bit. Or the second variable is their math standardized score, right? So why math? Just because you can measure math, so it's slightly more quantitative as compared to any other test that you would want to do, for example, in social science or in English, for example. Okay? These are my words. I don't think that went behind designing this study. But is the data set clear? So I'm going to show you what the data set looks like. So the data set has different IDs. There is gender for male, female. There is a math score, and the second last variable is the number of days the student is absent and which program he or she was enrolled in. So there are three different programs: academic, vocational, and general. The idea is we want to model can we predict the days that a student is absent in based on other things. Also, if you're in class and if I'm allowed to use laptops, but I will request, unless I tell you to use laptops, I think there's no reason for you to use laptops. So I will have to request you. If you have work, you can either move out of the class and do it, or if you want to stick around, please close your laptops. Okay. Okay. So how do you go about modeling this? How do you go about understanding this?
Just a question.
Yeah.
What is the math column represents?
This is the standardized score as to how well they have performed in a particular math class and so forth. And this is done towards, of course, it's not exactly clear when was this measured, was it after or was it before, but you can assume that this is somehow reflective, a quantitative measure that you're getting from a student. And it is something that's going to somehow get related to the number of days a student is absent. Okay? Any other questions about the data? Okay, how will you handle it? Or so goal is clear. So the explanatory variable is, finally the chalks are here. The explanatory variable is this is what I want to model, and I think this is going to be a function of, to begin with, maybe just the math. This is the simplest model that you can think of. Y as a function of x. Okay? Any other model that you can think about?
It should also depend on gender.
Okay, fair enough. So, and how?
Because there is a myth kind of like males are more engaged in mathematical stuff.
Oh, okay. Well, I think that has something to do with the way we have differentially treated women. So I think we'll not go there. But okay, possible to have a gender effect. Yeah. Program. Okay, so that's another model.
So gender can be related in a way that if the groups are larger, they have the possibility to cover up the missed class. So if there are two males, they know that if we miss, they will not have anyone to talk to or discuss. that can also be there. Like if they have a safety net, they will be more likely to.
Okay, that's a good point. I had not thought about it. That's wonderful.
What are the categories involved in program?
There are only 3 categories: academic, vocational, and general. And I don't know the specific definitions of these, but I think vocational is something that you're taking as a side kind of a thing. Academic is something that's like your core course, yeah, something of that sort. Okay. Any other models that you can think about?
So maybe before moving into the regression kind of thing, maybe we can individually look at, for example, just look at the days absent and gender, and then look at the percentages.
Okay, great. That's very very true, right? So before we do any modeling, right, while our goal is that we are interested in finding out if attendance behavior is different across different programs and different math groups, and how it relates to the math scores and so on. I did not explicitly put gender here. We'll do the example here in this class. But what I should do here, right, so the question is clear, right? Like I know what is the question that is being asked. Before I do any kind of analysis, the thing that I should always check is what does the distribution look like, right? So the first example, for example, I could look at is, and I'm going to make use of my Copilot here, because why not? It looks at, I don't need the extra stuff because I know what I'm doing. So this is the distribution that you have for the number of days that you're absent, right? So this is just a simple histogram. It shows that most people are actually not really absent, but there are a few of them, which is a kind of a long, slightly longer thing. I could also just look at what Sahil said. Name is correct? Yes. I could also look at how does this distribution vary across different groups that I have. Okay, let's see if it is getting it right. It seems to be doing what I want. So I will, well, actually I don't want the histogram. I want the box plot, for example. And I will remove the other stuff. Okay. So I just want to look at, for example, that how does it vary across different academic groups, and of course you can see that there is a clear distinction that general has slightly higher compared to academic and vocational, which probably I think they take out of interest. All right, again, I don't know the definition of vocation here, but that's something that you clearly see there's a difference. Now let's split it based on gender as well. I'm just going to copy this and change the gender. So it's different, but I think not so different actually, right? Like it seems that the distribution is very, very close. You can of course test whether there is statistically significant difference or not, but ballpark it looks very, very similar. Okay. So we have done one pass of just looking at exploring the data. We know what the distribution of the days looks like. This is what we are interested in modeling. We will let's stick to a simpler model for now, because we can cover one more thing that we could have done after I looked at this data is I could have just said that, hey, I don't really see any differences in terms of the gender. So I will probably, it's okay, maybe I just use this model as my model. Right? So which is the model that I'm going to use now, which is the days absent is just a function of the math score and the program that you're in. Okay? Okay, so how would you go about, actually there is one more step before we think about a model. What should I do here? Before I fit any model, what else would you like to see what I have not shown you yet? What else would you want to check? Any other things that you would want to just get a glimpse of?
NaN value present or not?
Okay, we can check for NaN values. So we can check for NA values here. It's nothing there. And I think it should not be there anywhere else. Maybe you can write a better code to do this, but right. So everything seems to be more or less complete. Anything else that you want to check?
Out of total samples, how many are males and how many are females?
Okay, we can check how many number of males and how many number of females. How would it help in your model?
So this maybe so the way I was thinking about the groups and all.
Yeah.
I was still thinking in that direction. Those groups are small and some group is small. It might affect that. But it is already looking like the gender is
It
not-
looks
yeah.
balanced-ish, and in a good way. So, okay, that's still a good thing. Actually, I had not thought about it. So it's an interesting idea that how does the group size have an effect on the overall trend. Anything else you want to see before we actually run a regression? So you know how to run regression, right? You can just do LM, a linear model here, right? So in R, if you want to visualize, if you want to visualize what, or if you want to fit a model, I will just do LM, and this variable, which is your y, which is a function of x, and of course I can keep adding different variables here. It's very, very simple. But before you do this, is there something that you should just check? You should just see, should visualize.
We could check for homoscedasticity and heteroscedasticity.
Okay, how will you check for that?
There is a function in
So
So we lowered the dimension and plot inside.
it's already low dimension. We'll cover the dimension. If we have time, we'll cover the lower dimensional stuff in this class later on. But anything else you would want to see, like very simple plots? Any one plot which is missing right now, which you would like to see? Scatter plot, right? Okay, let's look at few scatter plots. So I want to, for example, see what does. It's very, very smart. I think it's hearing what we are saying. Pretty sure actually it's hearing. But on the x-axis, I am plotting the math scores, and on the y-axis, I'm plotting the days absent. It's colored by program, and it's just to see what does the distribution look like. Okay, and this is what the distribution looks like. Any patterns you see here? I could also, while you're thinking, I could also try to be slightly more fancy, and let me see. Okay, let's see if this works. Okay, so now we have everything that we want to visualize. We have the program. I will just increase the alpha because it's otherwise like. So what I'm essentially doing here is alpha, just to give you what exactly I'm doing, right? So I plotted, of course, this is just a scatter plot, but of course you can see that there are points which will lie above each other. Alpha just reduces the opacity of these points. So if it is 0.5, this will become slightly lighter, and if it is 1, it will become darker. It is a good practice if you have a lot of overlapping points. That's what alpha is used. I'm just coloring it based on the program, and I'm distributing this based on the gender. And wow, so people who just came to the class now, like why are we doing this? Because somebody in the morning asked a question about is there an attendance? And of course people don't want to come to the class, which is totally fine. We are interested in if there has been some study on what impact attendance has, what impact scoring in the class has on attendance, right? So we are flipping the question a bit because I would want you to take the message home, whatever message you want to take home. But that's the question that we're trying to essentially analyze. Okay, anything else you want to see before we actually get into the modeling part? Anything else? Good question. So there are some outliers, of course. You can see that there are extreme values. So before I run regression at this point, like when I do the scatter plots, I don't see that trend in both the variables considered together, right? So if I had seen, for example, in here, if I had seen, again, all of this is very subjective, but from the looks of it, right, maybe, like maybe this point is somewhere outside, but everything else looks okay actually. So I would just probably keep it. If you wanted to be really, really finicky, you could say that for each of the variables, I know that this data set is prone to outliers. I'm going to throw away the top 0.5% quartile and bottom 0.5% quartile, because maybe those are outliers. But it's a very small data set to begin with, so you will also lose information in the process. Yeah.
So actually, how many data points are there?
How many data points are there? 340. There's 314. So the data points are 314. Okay. Anything else you would want to see?
The dependence is mostly till 50. Like after the dependence between days absent and math score is more in the initial, like in 50 months. Later on, it seems like doesn't matter. The absent
Okay. So it's good. Actually, now this side by side is very good. So given that you're seeing what you're seeing, and everybody else also seeing, intuitively what model do you think you should fit? And for that, you need to know what is the meaning of each of these terms, which we covered in the last class, but I'm going to cover it again. So put that into a thought. We will, as the tangents we take in the class, I'm going to take a tangent, go back to the slides, and then ask you to think about how to actually think about this model, right? So in this model, we have to think about this as a function of math and gender. In this model, we have to think about days as a function of math, gender, and program. Intuitively, what is this model, right? Like, so for example, between this model and this model, what is different? Like, what is happening differently? If I can also fit this model. Let me fit this model, okay? And let me plot a line. So I'm letting Copilot help me do stuff, because I know what I want, and it's perfectly fine if you know what you're doing. Sorry. So in the first code, what I'm doing is I'm just fitting a line. In the second, once I fit a line, that's the model. I'm just asking that model to predict what did you fit. And I'm going to use that to make a line, because that's what I'm fitting, right? So again, thanks to Copilot, I don't have to do much actually. Okay, now I got an error, so I am in trouble now. I see. Okay, so this is the same plot, but now with this, you see this line, right? So this line, black line that you see, is for this model. How would I change? How would it change? For example, if I were to use model number 4, what would change intuitively? This is model number 1, model number 2, model number 3, model number 4. How would it change? This is the one black line which passes through your data. This is what you're fitting. If I were to switch the model and have this as my model, intuitively before we do this, what would this plot look like? So let's think about this model itself, right? So what is the intercept of this model? What is the intercept? So while I'm fitting this model, but in R, when you do this, the intercept is implied actually. So I should have made that clear. But what you're fitting essentially is this is implied. If you don't want it, you have to explicitly tell it that don't fit and intercept. Let's do it actually. Best way to learn is to do it and see what it makes like. So I had an intercept which is implied, but I don't want intercept anymore, and this is the line that I get. Okay. So now I told it I don't want intercept. So the intercept is 0, and this is the line. You can see how what changed. The relationship has totally flipped. Okay. With this intuition in mind, let's go back to our original model. So what is the intercept here? What is the intercept in this case?
Somewhere around 10.
Yeah, somewhere around 10. This is the intercept. And what is this? This is the slope. Intercept is the amount of value or the amount of days absent. So by what does it mean physically? It means that even if I score 0, right? Even if my math score is 0, I have a tendency on an average that 10 days that particular student, even if they have a score of 0, will be absent in the class. That's a baseline. That's what the meaning of intercept is. What does the meaning of slope here? Let's look at what the model tells us. Let me first show you what the. So in R, if you want to learn what the model is doing, you just do a very quick thing, which is summary. And this tells you that this is your coefficient. So 9.11 is your intercept. Minus 0.06 is your slope. These are the standard errors. What does this imply? What does this mean? We saw it last time. What are these different things that you're seeing here? So standard error is the standard error is the standard error of the mean. This is the mean estimate that you got, that if you had done multiple different samples of this data, the mean that you're getting would have hovered around this particular value by this much standard error. This is the t value. This is the t statistic you can calculate because you have an estimate, and you know this is the population mean, and if you divide this by standard error, that follows a t distribution. This is from statistics. And finally, you have what is this? This is the p value, right? So our null hypothesis in this case is there is no relationship. So this should have been 0, but we see minus 0.06 and the p value is minus 4.28. So just to revise where we are, like this is the p distribution and this is your minus 4.28, and you get a p value which is less than 0. In this case it's it's not a pair, it's not a, your alternate is not directional. So this p value represents what is the area covered here and the other extreme, which is very small. So we say that this is significant. Okay. So this is significant. This means that the slope is true. Okay. Now, can you tell me what is the interpretation of this? Like, how should I understand this? So fine, I've got a slope of minus 0.06. But how should I explain this to a policy maker? Like in your plots and everything, like you can write the equation, but to a policy maker or to anybody who does not actually understand regression, this does not make any sense. Like fine, it's an equation, so what? So how should I explain it to somebody?
You can also
Yeah.
you can conclude that as the score is increasing, the days of absent is decreasing. So
Fair enough. So as with on an average, if you are absent, if your math score is 0, then you get an absent days of 10, and for every 1 unit score rise in math, your days of absenteeism decreases by 0.06. That is the physical interpretation of what this plot is about. Okay. Any questions about this? Okay. Good. So we will flip, and I will let you read this slide without actually explicitly, because of course this is slightly old, this is done in a school setting and so on, and I don't want to read it aloud. We are welcome to read the entire report. I just got this morning because of that question. It's interesting. You should definitely look into look into it, right? But from habits hard to break, a new look at truancy in Chicago Public High School. Students cannot perform well academically when they're frequently absent. Whether it's true or not, I think you are the best judge, because whatever works for you is good, right? So I'll stop there. We will revisit. The goal here today is to cover what are called generalized linear models. We discovered, or we saw last time, that we had something called linear models, which is what you see on the board. But linear models are inherently good and simple models, but they're also very limiting models because they don't actually give you the freedom to model everything that exists in this world. So we're trying to go into generalize it. Before we do that, we have to revisit some of the things that we skipped last time, which is, well, there's a lot of equations here which you don't have to worry about. One thing that I want to highlight is there was this residual standard error which we touched upon, but we didn't talk about it. So the residual standard error is simply the standard error of your residual sum of squares. Residual sum of squares is essentially the sum of squares of your residuals, which is simply yi minus yi hat square. This is your predicted version, and this is your observed value, right? How much deviation do you see once you predict, once you fit your model from your observed values? And we can calculate a standard error for that as well. This is what your RSS is. We also talked about confidence intervals very briefly, and the reason these are important is because any estimate that you draw, linear regression, while you're doing a linear regression, but it's a statistical model. With any statistical model, your estimates will have confidence attached to them, which essentially is a reflective of that. If I were to repeat, for example, if I give you a 95% confidence interval, what it means is if I do 100 different samples, around 95 of them, the mean estimate of the slope, for example, will lie in this particular interval, which you got from this experiment. Okay, does that make intuitive sense? Confidence interval. Any questions about this? While there are formula, we'll focus on the interpretation part. Like this course is, it's not a, while on the net it says it's a statistics course, but it's an interpretation course, right? So this is, we will focus on the interpretation part of it. Okay, so the linear model is this we touched upon last time. It's testing a very simple hypothesis. Beta 1 is 0, is your null hypothesis, and beta 1 not equal to 0. We mostly care about the slope. The intercept is not the most interesting part of the model. Well, in this case, we did see that the intercept matters because it can actually flip your slope depending on what you're forcing the model to see. It follows a t distribution, and because we know what the distribution of the t distribution looks like, we can calculate the t statistic. In this case, your beta naught is 0 because that's your null hypothesis. If this value is significant, we say that the slope that we identify is statistically significant, hence it has meaning overall in the data. Okay, how do you assess, right? So this is all good. We have a linear model, we have some ways to describe the data, but is it a good fit or not, right? So I showed you, for example, this kind of plot. Is it a good fit? How do you assess whether it's a good fit or not? So very simple metric for a lot of linear settings is what's called the R square, which is written as the capital R square, not the small r square. The capital R square essentially is how much total variation do you have, which is your total sum of squares, minus how much you have explained from the model divided by the total. Okay? So the TSS is simply how much your value deviates from the mean value. Okay? RSS is how much does this observed value deviate from the predicted value, and this is a measure of how close or how different these are. If you simplify this, it boils down to this, right? 1 minus RSS by TSS. If this value is 1, which essentially means your residual sum of square is 0, which means it's an extremely perfect fit, right? Whereas if it is 1, then your model is not doing anything, right? Your model is, if it is 0, which means your RSS by TSS is 1, your model is as good as like a random fit line. It's not actually helping you explain any data at all. Okay, and I have no idea why it's okay. Any questions about this? Why is it capital R square? Why not small r square? Why did I emphasize on that part? Okay, people do confuse this with correlation coefficient. So you have all seen correlation coefficient, right? What is correlation coefficient between any two variables?
Covariance of x by sigma x sigma y.
Okay, so correlation measure is essentially a measure of how do these two values co-vary. Okay, so this is your x, this is your y. If I want to measure how they co-vary, I need to be able to understand or quantify on a basis what does overall, don't worry about the formula. How does each of them, there's formula on the next slide, don't worry about it. This is just for the intuition sake, and there is a y analog equivalent for this. We are essentially interested in, does x predict y? So if correlation coefficient is 1, it says that I can easily predict y because it co-varies. It is totally related to my observations that I see in x. So this is calculated using different metrics. Mostly you will focus on what's called the Pearson correlation coefficient, for which this is the formula. It's the deviation of x and y from their respective means divided by how much does x vary on itself, how much does y vary on itself. Jointly, how much do they vary from their respective means divided by how much do they vary on their own. Right? So if they vary perfectly like this, then that will be 1. But of course, if they don't vary, that will be close to 0. And if they go in the other direction, then it can also have a negative value. So its range is from -1 to 1. This is the small r, which is the correlation coefficient. So this has a special meaning. However, in the case of a single variable and in linear settings, your capital R square is equal to R square. So the amount of information that your model explains is equal to the correlation coefficient between the two variables if it is a single variable data and you're fitting a linear model. You can calculate R square for any model. It's not tied to a linear model. Okay. This quantity, which is TSS minus RSS divided by RSS by TSS, can be calculated for any model that you fit, because the definition is generic, there is no assumption. The R square here itself does not have very strong, the correlation coefficient also does not assume any distributional properties because this is all empirically defined. They become only equal in the case when you have only one dependent variable, okay? For simple linear regression, in other words. Any questions about that? So in the model that we did, it will also predict what is your R square, right? So this is your residual standard error, this is your multiple R squared, 0.05564, it says, and it is in this case, we'll talk about the adjusted R square in the next class. When you have multiple variables, this quantity actually scales with the number of variables that you have. You need to do an adjustment if you want to compare two models. For this class, it does not matter. We'll talk about it when we explicitly talk about model selection. Okay. I could have also, for example, just to give you a flavor of what we are talking about, I could also simply do correlation of and that's -0.23. I will square it, and that's 0.556, which is basically equal to my R squared in this case. It says multiple because it's generically written, it's not written for this case. This is, by the way, a simple linear regression, only one variable. Okay, is that clear? So these are things you can, of course, verify very, very quickly. Okay, so the one thing I wanted to take with you always is that while metrics, you can always calculate correlation and you can always do things, but they actually don't mean much sometimes because the data that you have is very context specific. You should always visualize data. For example, This is an example taken from a 1948 paper, I think, where the correlation coefficient is similar, or actually in this case it's the exact similar coefficient. However, the distribution between x1 and x2 and x1 and x3, x4 is very, very different, right? So while this and this has exactly the same measure of correlation, they have very different meaning when you actually start to interpret the model, right? You would want to fit something here, but I'm not sure if I'd want to fit something here at all. Okay, so that's something that you have to always visualize the data and get a feel whether it's worth doing or not. And then there is a classical example of correlation coefficient also not having very special meaning. Any idea about what is the correlation coefficient for this case? It's a guesstimate. Let's do a guesstimate. X, Y, what is the correlation coefficient here? Correlation coefficient is a measure of how much can you predict Y from X. Here, how much do you think? Both, at least the direction you should be able to guess. Magnitude actually in this case is easier, but direction maybe not so much. What is the magnitude? The magnitude of R goes from -1, well, the magnitude goes from 0 to 1, the sign can be minus or plus. The range is -1 to 1. In this case, what is the average? What is the correlation? Yes. 1. Okay, why 1? Okay, so let's think about it, right? So my x is increasing, right? In this direction, if I go, my x is increasing. Can I predict my y? I cannot. It's hard. It's kind of 0, right? Why? Because if I go in this direction, this is increasing. But if I ask you to predict y, it can be anything. Like it can be this, it can be this, it can be this, like in this case. Right? So it's very hard. Right? So that's how the correlation coefficient should be instead. Okay? What about this one? Think about it again. You're going in this direction, you're going to say, can I tell you what is y? And I cannot. It's hard. Right? What about this one? Slant down.
-1.
-1. Okay. And this one? Okay. So let's see what it is. Any other guesses? Okay, 0 y 0. Okay, so here you're going, and it could, if I ask you to predict, it can be here, it can be here, it can be here. Anyway, we'll see what it is. Yeah.
For x there is only one y, assuming that I mentioned it's -1. If there are multiple, then it's
Okay, so you mean to say that this, and this.
yeah. If for one x there is one y, it's okay. But it seems that for a x it can be multiple values. Then it's not a minus.
Yeah. Okay. Does everyone see why it should be 0? Okay. What about this one? White lines. Again, hard, right? Like if I'm here, I cannot say anything about y. I can only say it's going to be 0. If I'm here, it could be anything. Hard, right? So always visualize your data to get a feel of what is it telling you. Data speaks for itself once you visualize it. Okay, so this is a visualization taken from this package called Datasaurus. Look at the mean. Mean is not changing. The first 2 digits of this mean are not changing. Neither is for y mean, neither is the standard deviation. Only the last 4 digits, last 5 digits, I think, change. And because of this, all of them have almost 0 correlation. Okay, but you can fit whatever you want. And if you do machine learning, you can just feed it and it will give you something. But does it make sense? That will only sort of come from actual visualization. It's a dinosaur. You can make a dinosaur out of this. Okay, any questions about this?
So, realistically possible.
Yeah, it is possible. Yeah. You mean this kind of data? Yeah. You see this a lot actually. You see this a lot, and in fact, this should be the entry point for any data analysis that you do. Just simple scatter plots to help you visualize. If you're working with 2 or more variables, just take one variable at a time, visualize what does it look like. And that will tell you a lot about, is that problem even worth modeling? Is that problem even complex worth applying an ML model? Is the problem worth even applying a simple model, right? So those are the questions that should be answered.
But among these plots, for example, that the 2 circles, that is actually a valid place to go about. Like there is a distinction. Like there is.
Fair enough. There are 2 classes. Like if you think about it from that perspective, yes, that is correct, right? But in this case, I did not tell you anything about the classes of these data points. His point was also clear about some. Sorry. Final clarification. So if I told you, right, so this example, by the way, one of these examples you've seen in the first class, which I will talk about at some point, which has to do with happiness and where, right? So all of you saw this is wealth. This is also going to be an assignment actually. I don't have to discuss it. You will find it out for yourself after this class. Right, so we did an example of this where we showed you that there's a negative correlation. But I also showed you that there is something about these points, right? Like in terms of, if I gave you access to what is special about those points. For example, in this case, they might belong to a particular age group, for example, or these points could belong to an age group and so on. If you have that information, then yes, that's a valid point. But if you don't have anything, and if you're if there is no other source of variation or variable in your data, and you get something like this, then it's a good stopping point, because it seems there's no structure in the data. Unless somebody told you that those 2 circles are there because they come from 2 different classes, 2 different batches, 2 different individuals, 2 different cohorts, or so on. Does that make sense?
Yes, but
You're not convinced. Okay, yeah, go ahead.
But okay, let's forget that there are classes. Let's just assume that there is. So in these cases, there is not a one-to-one mapping in X and Y. So there are multiple. It's going to multiple.
Yes.
So
Yes.
also, like the correlation of basically it's the Pearson.
It's the Pearson model.
It
Yes.
doesn't capture. It's not made to capture these kinds of relationships.
Fair
We
enough.
should not stop.
Fair enough. Right, so it's a very contextual question that you're asking, right? So in terms of, if I have to fit a linear model in this case, I would not go ahead with it, right? Yeah. Right, fair enough. But if I have to maybe think about this, that, okay, maybe in these 2 variables there's not structure, but if there is other variable which I'm not able to see right now, and which my machine learning algorithm should be able to figure out and tell me what is the right feature, then maybe I will go ahead with it, right? So it's a very specific question that you have to ask, whether the model and the data that I'm visualizing, are they doing justice to each other, right? So for example, if I go ahead with this model trying to fit the circle, it will give me something, but it doesn't make any sense, right? Maybe the slope will be maybe not significant, but like to start with itself, it doesn't make sense, because I don't see anything, right? So why should I even force a model to fit like this? Does that make sense? Okay, so we'll talk about, we'll get started with GLMs, right? So let me ask you a very simple question, and apologies, there's a typo there, but I think hopefully it's clear. It's represent. What is the right model to represent this data? This all of us have seen at one point. These are the number of COVID cases. X-axis is the number of days. Y-axis is the number of cases detected, non-cumulative. How would you model this kind of data? Exponential. Okay, so what model should I write?
Number of cases is proportional to related.
Okay, cases is
Number of e to the power
e to the power number of days. What is the model? What is the coefficient? So I want to learn what? Eta? This. This model. Any other ideas? Yeah.
It will multiplied with days in the exponential power.
Exponential power, there will be what?
Another multiplied
Day square.
coefficient, another coefficient.
Oh, I see, I see. Okay. You mean e to the power beta days
Yes.
plus beta naught. Okay. Any other models? Any other model? Okay. Now, question to you: which one of these are linear models? Okay. This we cannot solve in this class, but let's try to see if we can. Okay. So far, we have only discussed this version. While we cannot explicitly discuss that, there is a formulation we can change a bit and see whether we can come close to modeling it. I think both of them are decent in their own space, and there is no one right model or the other model unless you actually have metrics to prove. I don't have right now to tell you which one is going to be right. At some point we will come to that example, but it's a good starting point to think about will a linear model fit, right? If I just do a simple LM, linear regression, will that fit? Or is that sufficient?
It should fit, but it might not be sufficient.
Yeah, it will fit, right? There will be something which might fit. I don't have the data right now. We'll do this in the next class. We will, I have the data somewhere, but we will come back to this in at some point. Okay. Okay. So let's just revisit OLS and what are its limitations. OLS is ordinary least square regression, or your simple LM fit that we did. There is a lot of what are the assumptions of a linear model? What are the different assumptions that we usually use in OLS?
4 assumptions by.
Okay, yeah. What are the 4 assumptions?
First is there will be linear relation between the parameters and the observed value.
Okay.
Second is the independence between the observed values, that they will not be dependent on each other.
Correct.
Third is the normal distribution, like the residual errors should
Yeah.
be normally distributed.
Yeah. So those are the 3 main distributions that you have, and of course you have the the homoscedasticity assumption, which is there should be a linear relationship between the outcome variable and and each covariate. They are independent observations. They have equal variance. The errors are normally distributed, and they are homoscedastic, which I already talked about. Now the problem, however, with these assumptions is while these are good to start with some data, they actually don't fit with all the data, right? So let's again go back to this intuitive picture that we had drawn, and I've expanded this now to give you slightly more intuition as to what is happening. Intuitively, when we fit a linear regression, what is it that we're trying to model? We are trying to model that can I, from assuming the errors are normally distributed, which is the core assumption that we have, what is the conditional distribution, right? So how is my y distributed given I gave you x and my errors are Gaussian? Is y also follows a normal distribution, right? So when I write this model, which is x b plus e, these e is normal, 0 sigma square, and the probability distribution, this means conditional, which means that how is y distributed given I gave you access to x, which you are able to observe, also follows a normal distribution. In a sense, what we are trying to do is we are trying to learn what does this mean by fitting that line, right? So it hovers around this, right? So this is its mean, this is its standard deviation. We are trying to essentially pass a line because we are trying to essentially learn the mean distribution of y as a function of x. Okay, this is what we do in linear setting. The reason sometimes this is not sufficient is because maybe this assumption that all of this variance is constant will not hold, right? You already seen one example in the class beginning. It's seeing that there were a lot more variation in the less math score as compared to higher math score, right? So we can fit it, we can fit the linear line, and again you will get some value. But is it the best model? Maybe not. And this is the way to think about can we do slightly better? How do we do slightly better? We introduce this concept of generalized linear models, right? So linear models are trying to assume a linear relationship between the response variable, which is your y, and your explanatory variable, which is x. Y is assumed to be normal, and we model the linear function of the mean, right? So when we fit this model in your LM function, essentially you're trying to understand how is the mean distribution of y distributed as a function of x. Okay? And this is the line structure that we are trying to do. Generalized linear models are a superset of linear models, right? So the linear model, in other words, is a very special case of a generalized linear model, which models the distribution, the response variable. There are three important components of a linear model. One is the response variable, right, which is your y, which is again not news, you have seen it. But we also specify how is it distributed. While in the linear model case, we assume that it is going to be normally distributed because everything else follows from that fact. In the case of generalized linear models, it is something which is generic. We will see how to think about how to model this. Okay, y can follow, in other words, simple terms, your y can follow any distribution in the world. It is not forced to follow a normal distribution, which gives you a lot more power to do very interesting things, and we'll see one of these examples in just a minute. We explain with the explanatory variables have a linear relationship, of course, right? So beta 0 is your intercept. You have p or j linear p explanatory variables. You will still model them as a linear function of your parameters. It's still linear in terms of its parameters. Okay, that's why generalized but linear. Still linear in the function of its parameters. And then we have an interesting thing, which is actually what makes the innovation happen. The innovation here is, rather than modeling y, or rather than just modeling the mean of y, which is what we have been doing in the linear regression, we say that the mean is not a linear function. Like the mean itself can, a function of the mean itself follows a linear model. Okay, so there's a clear distinction here, right? So in this case, I was saying that the mean of my linear model follows is linear with respect to its parameters. Now I'm saying that no. In the I can also do this. I can apply any function g. That g is the link function. I can apply any link function and model the mean, and that brings the innovation that we're going to just see in just a bit. But does the idea make sense? Rather than modeling the mean as a function of your explanatory variables, you're modeling a function of the mean, g. What is this function? We will see in a bit. Y itself has been relaxed in the sense that it does not need to follow normal distribution. It can follow any distribution, and g can be any function in this world, but there are certain interesting functions. If you use them, then the math and the derivation of these parameters becomes simpler, and they are what's called a canonical link function. Why are they canonical? That we will not be able to cover in this class, because that requires some derivation, and it gets slightly deeper than I would like to go in this introductory class. But all you're doing is you're bringing a new function, you're modeling the mean of your data, and you're saying that that is a linear combination of the explanatory. Okay, is that intuition clear? Okay, it's very confusing. Huh? It's very confusing, right? So let's clarify some confusion. First, let me show you what are the link functions. The link function for different distributions are different. This is, by the way, taken from Wikipedia, which when I was studying, I was told that never rely on it, but I think you should rely on it. It's pretty good. The distribution can follow, it can be a normal distribution, which is your usual linear model. So in this case, this distribution is what y is following. So y itself has a distribution function, and then the mean is related to y by the g function. This function is the g function. It tells you how should the mean itself be modeled, right? So for example, in this case log, if I take the log link function, rather than saying that y bar is equal to x beta, I am saying that ln of y bar is equal to x, right? And in this case for Poisson, my y follows a Poisson distribution, and log of the y bar follows a linear model with respect to the covariates that I have. Okay, does that make sense? Any issues, any doubts, anything? Any questions so far? Okay, I know it's very confusing, right? We're not getting any intuition, but how to very simply understand what we're doing. So the linear model is this, right? X beta plus E is your linear model, where we assume that E follows normal distribution, and because of this, ln yx just tries to model the mean of y as a function of x beta, which is going to be normal. In this case, GLM, we fit g of y equal to x beta plus E. G is the link function that I showed you, and this allows y to have any distribution. While this forces it to only have normal distribution, this y can have any non-normal distribution, including normal distribution, of course. So in my LM fit, I do lm y tilde x. In GLM, all you do is you do GLM, generalized linear model, y as a function of x, and then I specify a family. What is that family? That family is the name of the distribution that I think y follows. Again, I don't know what distribution it follows, but you need to have some context of the field to know. For example, counts are always modeled using a Poisson or a negative binomial random variable. Continuous values, for example, are Gaussian is fine, gamma is fine, and so on. We will talk about this in the next class in slightly more details. But this is how you specify what is the distribution y follows. And finally, you specify what is the link function. What is that g that you're going to model so that you can capture the entire variable. Okay? Is the idea between a LM and a GLM clear? The only way to understand this is actually look into what happens if I fit a GLM or a LM. Okay? And in some version or the other, if you're familiar with logistic regression, that's one of the simplest GLMs that exists out there. But how do we understand this, right? So the way to understand this, actually before I show you, why should I care, right? Why make my life so complex with giving you a distribution function, giving you a link function, and so on? The reason we like GLMs is because, in very simple terms, LM is very constrained. Yes? Yeah. Yeah. Interesting question. So if you plot a function of g of y, yes, that will be linear. G of y is a linear function of your x's. So once you learn the parameters, if you plot g of y, you know what is y, and if you plot x, you can do a linear fit in that space. Yes.
And then we take an inverse, then that will become one.
Correct. Yes, exactly. So when you take the inverse, that's where, in some sense, the non-linearity comes. I will show the plot and it will become clear once you see the plot, right? So while we are still fitting a linear fit, right? The model itself is linear, but when you plot the final curve, right? Is that what your question is? It will look slightly non-linear. And the reason it is because in a different space, for example, in a log space, it is linear, but in the original space, it has become non-linear, because it went through a transformation in the process. So there is a subtle difference that the model itself is linear, right? But the observations that you're able to now capture, you can capture non-linear relationships in some sense. It's not like a straight line that will always fit in this data. Once you visualize it, x versus y. Does that make sense? Let's do a quick example, and I think this the best way to make this clear is to actually do an example. Okay? So very quickly, why are we doing this? We are doing this because we want to, we could have actually, let me ask you this, like, let me go back to the slide, right? let me ask you this question from this perspective. This is probably a better way to. So you saw this data, right? You saw what is going on. Y is days absent. What distribution does it follow? What distribution does Y follow according to you? And it's okay if you don't know the name, but tell me about how would you see what distribution does it follow? You will not know the name, of course, because we have not discussed this. But how would you check what distribution, what does it look like? Is it normal? Why? What is the distribution of Y? What is the distribution of Y? How would I check? Any observations distribution, how do I check? I don't know what it looks like. I have no idea actually. How do I check? Louder. Mean. So I calculate the mean, is it?
Get the distribution by probability.
Okay, how do I get it? So let me first follow what Nikita said. So I will do mean. Okay, I got mean 5.95. So what next?
One way using code is get the variance, get the mean.
Okay, fine. Let me get the variance. 50. Okay, let me get the median as well. What is the quickest visualization I should do to histogram or density plot, right? So I could just do histogram. Does it look like normal? It's not normal, right? So you can fit the line. I fit the line already. I fit that black line. You can do it, but it's not doing justice to the data. It's not normal, right? It's just not there actually, right? So while you can do things, but is it the best thing that you can do, right? No, right? So if it's not the best thing, then maybe we can do slightly better, right? And in most cases, you don't have to worry about it because you just show a linear line, you're happy, and your project manager or whatever, your boss or whoever, your advisor is happy, right? You see line, it's all good, right? It doesn't matter. But is it the best thing that you can do? Maybe not. So that requires some thought, right? So what is a thought? Okay, I know that this is not normal, but why is it like this, right? Like why does it look like this? What is so special about days absent, which should tell you that it cannot be normal? It can't be negative, yes, of course, it cannot be negative. Anything else?
Can't be decimal.
It can't be decimal, it has to be integers, right? So it has counts, it is integers, and for that reason, like normality assumption, you can force it, but it's not going to follow actually. So if it is not going to follow, while as a teacher and my classes, my goal is to tell you that this model you should use this, right? But there's no way I will be able to do justice to your data, right? You are the best judge of what you think should happen. Some of it will come from just experience of working with data. Some of it will come from just reading things, right? So, okay, counts. Again, I have no idea. I've not taught you what is Poisson. I've not taught you anything. So what am I going to do? Which, assume that you have got the worst teacher in the world possible, right? So how would you figure out how to model it, right? So I'll just say search model counts. Okay, I'll just search model counts data and I will find something, or model counts data, and let me search for distribution. These are counts because these are non-integers, right? So it seems somebody has done a good job, made a website, right? There are some count data models, and I will probably just read through, what's going on, or maybe, I will go to my friend and see what does it tell us, right? Like, okay, so it's telling me that, maybe I can do some sort of transformation. I could probably think about doing a square root transformation might be used when data can be approximated by a Poisson distribution. So I have some hints to carry forward here, right? So let's do this actually. Let's do, and I will leave this as an exercise. Why? Okay, now does it look slightly better? Okay, So I will leave this as an exercise why certain transformations are useful to actually help you look data like normal. Now, why am I talking about this? Because this is what used to GLMs were invented in 1984. But before this, also people had to deal with this kind of data. Before this is what they used to do. They would like look for a transformation which would make the observable variable look mostly normal, and then model this, right? So, for example, let's do it actually. Why not? Very quickly. I will change my LMFit and LMFit2 to model this. So I am now modeling. So in R, it's very simple. I tell it that square root of days absent should be modeled as a function of the math score. I will have to create one more prediction. And just I am going to plot it. I am waiting for it to complete because I have gotten lazy once these methods have come up. Okay, you see the difference? So the black line is your normal linear fit line. Oh, actually, hold on. There's a mistake. So I asked it to plot the square root, so I need to square it again. Okay, there's a difference in what the line is being fit. The black line is what you get from a normal fit, and the red line is what you get from your forced normal fit. And of course, these things have changed. I can compare which model is better, and we'll talk about it very soon, if not in this class, which one is the right approach. But there's a slightly smarter approach, and that smarter approach is what GLMs give you, right? So the idea behind GLM is to help you generalize this, right? So rather than looking for the best transformation for Y, which will make it look like normal, you look for the distribution itself, that this is the right distribution for modeling this data, and then you bring the problem of GLMs and try to solve in your model. Essentially, if you force your linear fit, you're trying to force the expectation to look like something. Whereas if you do GLM, you have slightly more control because you know what function this follows, and you know what is the right function once you know the distribution property of I. This G is actually, somebody has already done the job for you. So if I choose, for example, Poisson, I know what G should be, because there are it's the canonical function that I have to use if I force my distribution, because everything else will follow from there. But the GLMs broadly, they're trying to solve this problem that you don't have to transform your data, you keep the data as it is. Yes?
So in the previous slide, the data distribution was without being forced to be normal. We could have just simply fit lambda e to the power minus lambda x and train for the lambda.
You mean Poisson?
Yeah, it's kind of like exponential distribution.
Okay, you could do that actually.
So in that case, linear would not have been the best choice. The exponent.
No, so that is correct. So if it is a univariate setting, what you're saying is correct, right? You would model this as a Poisson model. But what I want is a predictive model or a regression model, right? So how to bring that Poisson nature into the regression setting is what GLMs allow you to do. What you're saying is correct, that if I saw the distribution, I will just plot a Poisson and I will get the parameters of that lambda, and I'll get it, right? Maybe, well, if you now mention it. So this is slightly risky territory, but I will do it anyway. The risky territory part is I have to recall, but let's try. Okay, so you want to fit. So I am slightly handicapped, but I will use a package which I know works, and Poisson?
Not exponential because it's decreasing.
Okay, but it is continuous. Okay, so I got something. Let me see. Okay, it doesn't have, 1 second. I see. Okay, let's go ahead. Okay, I see. Fine. Okay, so it fit lambda with 5.95. So again, by the way, this I had forgotten, but R's functions are so well documented that I just have to read and I can just do it on the go. Okay, so I will now plot this function. So I will, this is okay, and then I'm going to wait till it helps me, and that looks correct. Okay. Actually, that is, I think, going to create trouble. 1 second. This is correct. This is correct. Okay, 1 second. Okay. Okay, that should work. Okay, so this is what I get if I try to estimate the parameters. We have not covered this, by the way, in the class, so don't have to worry about it. I will give you an assignment related to this now, though, that this question has come up. This is what the original distribution looked like, and I learned the parameters using some method, and now I'm going to show you that if I learn the parameters correctly, what does the distribution look like. And you know, it's close. It's not fully there, but it's close, right? So if in principle you wanted to learn this distribution, you could use this as well. What this will not allow you, however, to do is to do the prediction, which means that it knows nothing about my math score, right? So it will not be able to do that prediction angle. Okay. So we have 7 minutes, and I think that's good to motivate how to actually solve this problem, right? So now you know that R is this Y is definitely not normally distributed. So how would you think about it? And you also know Poisson is one way to fit the model. So how should you fit? What should you do, right? So what I'm doing here is I'm fitting a linear model. This is just LM Y as a function of math and program. When I do this, what am I doing? I am estimating a slope for math. I am also estimating a slope for program. So the slope is a function of the math score, but also a function of the program. And what is program? So program in this case is what's called a categorical variable or a factor variable. I have forced it to give value 1, 2, and 3. In some sense, what I'm doing is, of course, with this character level data, I cannot fix anything, right? But I can give it arbitrary numbers, 1, 2, 3, 3, 4, 5. There is some ordinality or some way of putting them in order. You can put whatever you want, 1, 2, 3, doesn't matter for this case. But I will have to do it because otherwise I will not be able to do regression, right? It handles mostly actually, but it's better to explicitly set the thing, which is what I did previously, which I skipped over, which is what I do here actually, right? So here I have assigned it a level of 1 to 3 with this particular, so I've actually categorically ordered it, and while this remains a character vector, when you feed it to R, it knows that there is an order. General is 1, academic is 2, and vocation is 3. It understands it internally. Okay?
Will it not actually affect in regression? Else we can use OHE also.
What is OH?
I mean, one hot encoding.
One hot encoding. Okay. Yes, of course you can use one hot encoding. In this case, internally, that is exactly what it is doing, right? So Well, if you if you brought that point up, what is happening internally is actually it's a good question. We should cover, right? So there is academic, there is general, and there is vocational. So when you order something, when you make a factor, if I make it the first level, by default it gets encoded as a 000. So everything is with respect to this, and then this gets actually I don't need 3 bits here, and this gets this or something else.
So it's library that is doing it.
It's internal, right? So that's the power of R, right? That's why I use R for these things, because it is designed with these kind of use cases in mind, and that's why it actually works very nicely. While you can do this, of course, in Python as well, but
Explicitly do it.
huh?
You need to do it explicitly.
You need to do explicitly, or you used to use this thing that
Particular.
yes, which uses something called PATSY, PATSY, which was which has its own history, which hopefully we'll talk about at some point. Those are like it was still work in progress actually. The statistical learning part in Python is still a work in progress. Anyway, coming back to the question, right? So we have to fit a different model. Of course, this linear model, while might be great, it will not, of course, work. So there are 2 ways to think of it, and I'm going to make a slightly jump here because I've not told you about this distribution, but I did what you would do, which is look for Poisson model. What are models for modeling for discrete data? And Poisson is one of them. There is also something called negative binomial. We will cover about like why a negative binomial is required in some setting in the next class. But for now, just stay with me and say that okay, I force you to think that those are 2 models that you can fix, that you can actually fit in this case. Now, if I want to fit a Poisson model, I am doing GLM. I am doing the same function that I did for LM, but I am explicitly telling it that my Y follows a Poisson distribution and belongs to the log link family. Even if I didn't do it, R is smart. All these is also set by default. All I had to do is I could have just done Poisson and it would fit. And then I tell it that this is my data and it will fit a model. Okay. Similar thing with negative binomial. The unfortunate thing about negative binomial is when GLM was written, I think negative binomial is a tricky distribution, so its parameters had not been derived. So it's not encoded in the GLM library, but there's a separate library called glm.nb which uses it. So we will use that other package to run that regression. I will just take 30 more seconds and I'll finish. So I not talked about how do you compare these models, but a very simple metric is what's called AIC. We will talk about the formula in the next class. We ran a bit over time, but I will give you a flavor of how to compare it, right? So if you do AIC, which stands for archaic information content, the lower this content is, the better the model is, right? And here you see for linear, it's 2069, for Poisson, it's 2665, and for NB, it's 1721. So in this case, which model is better? Lower is better. So lower means the negative binomial model is better. Now question is, okay, fine, I have 3 models. I could have run this for 10 different models and I could have found out why a particular model is good. Why is it good? Why do you think is it better? How would you make sure that this information, which is a black box right now, your AIC is fine, it's low, but why? Why is it better? How would you visualize it, in other words?
Least error.
Okay, least error. Louder. What's your name? Vivek, yeah. Correlation coefficient, in what sense? Tricky thing to test, but potentially could be true. Errors is also one option. Other ideas? So I don't know. I don't know actually. I don't know the answer. But what I know is I can visualize this. I can visualize the model is doing. Right. So this is what I'm going to do. In this case, I will now try to predict for different models what does the fit look like, right? Now, one of the problems which I wanted to simulate and I was hoping would happen is in linear fit, there is no restriction of what y can be rated as, because y is modeled as a negative as a normal distribution which can also be negative, which in this case we know is not a realistic value, right? I was hoping that we will get some negative predictions. Unfortunately, we did not. It would have been a good example to show why you should not run linear regression. I failed this time, but next time I'll come up with an example where we will not fail. But here is what the different fits look like. Okay, so sorry, I'm just exceeding, but I'll just say, just 10 more seconds. This is your general category. So we have the line here. The dashed line here is what you see for the linear regression, right? So you can't see in most cases, but it does exist here. Similarly, we have another one. We are fitting essentially a different slope for different categories, and that's why there are 3 lines. Remember when we did linear regression with just our model 1, with just our model 1, I think I've lost it, but the model 1 was without any parameters, only math was the covariate. There we saw just one black line, which is this black line. But the moment I encounter different categories, now I fit 3 different lines here. It's not just 3 different lines, but they also have special meaning because they have a certain distribution assumption underlying about it. So I'll stop here. When we meet in the next class, actually in the next class I will encourage your friends also to come. I will go over some project ideas because this course requires projects. I will make an announcement and there will be a guest lecture. The guest is an internal guest. So Nigar, she's a master's student at KCDH and she'll talk about some of the work in public health and where some of these models have been useful, right? So all of this has been very dry because we do something in the class and then in the assignment is when you get the flavor. But when you do listen to that particular class, you will realize that these are the reason to go through this process is because you can apply them in real life. So she's going to cover her talk. That will be second half. First half, I will talk about projects and finish this material. Okay. Your assignment is due very, very soon. The moment that is that closes, the second one is going to come out. So just be ready. Okay. Okay.
So what did you just say, like last time?
The moment the assignment submission closes, the second one is going to come out. Okay.